Hello, welcome to another episode of Mystery Science. Today we're going to be looking back over CP6A through to E. What does that mean? Well, that means that I am going to be going through the content that's already in this playlist. If you haven't gone through the playlist, I recommend clicking on the button above you here, and that should take you to the playlist. What I want to show you in this video is just a very quick overview, a revision of these sections, and I'll go through which sections in a moment. This is targeted at the guys who are about to do a mastery quiz at the college that I teach at, and that's going to be tested on the following things. So the things we're going to look at in this short video are going to be atomic models and the history of the discovery of the atom. We're going to look at isotopes. We're going to look at the electrons and how they behave outside of the nucleus. And then we're going to have a look at background radiation and the types of radiation that we encounter. These are the short topics that are already in the playlist. Now, if you're watching this as I release this video is actually coming out before 3 of those videos on the playlist. There are already 3. There are going to be 3 more. Those are going to be produced over this weekend, hopefully. The reason this is coming out before those 3 episodes is simply because I think there are some that are already at the point where they're going to sit the mastery quiz just after the weekend. Okay, so a very quick recap then of the atom through the ages. Now, we know, because you've done the studying and you've seen my video before, that the atom has not always been the little buzzy thing that we know it is today. We actually thought of it before as some sort of spherical object that just cannot be divided anymore. Now, this is all very interesting and odd, but how did all this come about? And it comes because science evolves. Science itself changes when we get more and more technologically advanced. We use science to advance our technology. Then with that advanced technology, we change the science. We're able to discover more things. We're then able to build better technology, and we're able to discover more and more things. Where will this ever end? And the question is, we don't know, and that's the wonderful thing. Will it ever end? Who knows? And to demonstrate this point, the discovery of the model of the atom is a really good one for looking at, to focus on this kind of progression of science. And this all starts about 400 BC. In 400 BC, a Greek dude called Democritus, big beard, very nice, well-travelled gentleman, he thought to himself, if I take an object and I chop it in half, and then I take that other object, that half an object, chop that in half. I take the quarter, chop it in half. I take the 1/8 and chop that in half. I take the 16th and chop that in half. And you can see where this is going. You just keep chopping in half. Eventually, there must, at some point, form a particle, a small thing that I'm not going to be able to see, that I can't chop anymore. I can't half it. These things are indivisible. And the Greek, ancient Greek for indivisible is atomos. So Democritus, 400 BC, that's more than 2,000 years ago, thought about this and decided, yes, the world, the universe has to be made up of these tiny indivisible particles. And he wasn't wrong. But this is a thought experiment. He couldn't actually prove this for himself. He could just take things and keep chopping things, but it didn't really prove anything. He didn't actually do the chopping. It was just a thought experiment. It wasn't until the 19th century, in 1803, when John Dalton came along and said, aha, right, well, if I take this water, this well-known solvent, and I break it down somehow with my wonderful chemistry and my bubbly tubes, he found that every time he broke down oxygen, he always came up with the same ratio of 2 hydrogens for every 1 lot of oxygen. So he worked out very cleverly that, hold on a minute, every time I break down water, I get twice as much hydrogen as I get oxygen. That means that water, first of all, must be made of hydrogen and oxygen, which is correct, and that there must be twice as much hydrogen as there is oxygen, which is also correct. And so he was the first person to actually physically prove that a water molecule is made of oxygen and hydrogen atoms bonded together. Now this is genius. It proves Democritus' theory. Now, unfortunately, John Dalton then said, "Ah, spherical indivisible balls. They're hard balls that cannot be broken apart." And that was that for about another 100 years until J.J. Thomson came along. J.J. Thomson kind of went, I like to electrocute things. So he raised something to a very high voltage, put it in a vacuum tube, and allowed a stream of tiny particles to go across and hit a fluorescent screen. So he ended up with this little green spot. And then what he did was like, this is very interesting, but wait a minute. This is smaller than any atom that we know. And so he deduced, again, very cleverly, that these particles must be part of an atom. And they must be part of the atom because they're smaller than an atom. And then he put a positive plate above the stream. And the stream of these particles bent upwards towards the plate. The little green spot moved from the straight opposite the source up to the top. So he realized that these things are charged. They're negatively charged. They have an electric field. So he decided that these little things, these electrons, must exist within the atom. So he came up with the idea of the plum pudding model. He looked at the atom and decided, just like a plum pudding, it's a substance which must be positive with little negative electrons in it. Now he said that the substance must be positive because atoms are always neutral. They have no overall charge, like a neutron. And I'm not going to tell the joke because it's in my other video. But this means that he discovered the idea of the atomic neutrality, so there must be the same amount of positive charge as negative charge. So then Ernest Rutherford comes along, and Ernest Rutherford owns a laboratory at the Rutherford Appleton Lab. Now he, again, very, very smart man, even smarter because he got his students to do this. He got his students to roll out a very thin piece of gold. So he had a very thin gold foil. He then fired an alpha particle at the gold foil. And I'll talk about alpha particles in a moment. Now, the alpha particle should have either bounced right back again, because it's just going to have hit a wall of solid spherical particles, or it's going to punch straight through. And he thought, haha, we're going to get lots and lots of alpha particles detected on the other side of my gold sheet. So they did this experiment, and most of the alpha particles went straight through the gold, just as they expected. Haha, brilliant. But no, some of the alpha particles bounced straight back again. Now this is a little bit puzzling because that shouldn't happen. They should either all bounce back or all go through. But a very small number of them bounced back. And then, just to confuse things more, some of them were deflected. Instead of going in a straight path, they bent and they went down or they went up. They were being repelled by something. And so he realized, and the team realized, that most of the alpha particles going straight through, from this, they were able to deduce that actually the majority of the atom is just empty space. There's nothing there. But a very, very small amount of the atom, the nucleus at its core, is positive, because these alpha particles occasionally were being deflected by something. Now, positive charges don't like being next to positive charges, and so what happens when you put two positive charges next to each other? They push each other away. And so these gold atoms, the gold atoms, were fixed in place. They couldn't move. But these alpha particles were being fired, can move. So as they came along, they found another positive charge, and whoosh, off they go being pushed away. And if they came straight at the nucleus, they were then pushed back and repelled. So they discovered that the nucleus existed and that actually most of the atom is empty space with electrons floating around the outside. Have a look at my other video to find out exactly how much of the atom is empty space. After that, we end up with Niels Bohr. Niels Bohr comes along and looks at the shell model of electrons. He believed that instead of the electrons just floating around the outside randomly, like Rutherford believed, but no, they actually form different shells, and there are strict rules to these shells. And we'll look at those in the next portion. Now, here you go. Here's the Bohr model of the atom. I guess you could say it's quite boring. No. And then after that, Heisenberg and Schrödinger come along and make everything messy and decide, no, probability, it could be anywhere, anytime. So here are our models of the atom. You start out with spherical balls that cannot be divided. Then you get the plum pudding model, where those spherical balls have small electrons dotted around inside them. Then eventually we have the nucleus being discovered with lots of electrons randomly flying around the outside. Bohr then coming along and saying, nope, these random electrons are not random, they're in orbital paths. And then Heisenberg going, probabilities, weird maths, no. Before we move on to exactly why Bohr's discovery was really useful, let's have a quick look inside the atom again. We're going to have a quick look at isotopes. Now, what does isotope mean, Mr. E? Why are you coming at me with all these weird words again? Stop it! But isotope means it's the same atom. You have the same atom with a different number of neutrons. The nucleus of an atom can be different sizes. This carbon atom, there are 3 different carbon atoms here. One is carbon-12, the most common form of carbon. In carbon-12, there are 6 protons and 6 neutrons. So there are 12 particles in the nucleus at any one given time. These particles inside the nucleus are called nucleons. There are 12 nucleons inside carbon-12. See where we're going with this? The next one, the one in the middle here, is carbon-13. Surprise, surprise, there are 13 nucleons in the middle of this nucleus. There are still 6 protons, because if there wasn't 6 protons, it wouldn't be carbon anymore. In order for it to be carbon, it has to have 6 protons. The atomic number, the number of protons, determines what that element is. So for it to still be carbon, for it to be carbon-13, it's now got 6 protons and 7 neutrons to make up the 13. Now, this little bad boy right here, right next to me, that's carbon-14. Carbon-14 is the radioactive one. Carbon-14 is the one that we use to date things. If you want to know more about that, have a look at my previous video in the playlist. Carbon-14, as you would expect, because it's carbon, has 6 protons and therefore must have 8 neutrons to make the 14. So as we go up, they're getting heavier. Their mass number is increasing from 12, 13 and 14. So if you're asked what the difference between 2 isotopes is, it's the number of neutrons. And if they ask you specifically what's the difference between carbon-12 and carbon-14, for example, you can say, well, carbon-14 has 2 more neutrons than carbon-12. But for it to be carbon, still has to have 6 protons. Right, moving on to Bohr. Bohr came along and decided, right, atomic shells, electrons live in shells. They all actually have different amounts of energy. The electrons that are closest to the nucleus, they have one type of energy, and if it's further away, it has a different amount of potential energy. Now this can be explained when you look at A-level chemistry and A-level physics, because as the electrons are closer to the nucleus, they're more tightly bound, because they're attracted to the positive protons in the center of the nucleus. Remember, they're negatively charged. So they're flying around the outside and they want to be as close to the protons as possible. Now, the inner shell can only have 2 electrons, so those 2 electrons are very tightly bound. The next shell, they're also trying to get close to the protons, but there are these 2 electrons in the way. The 2 negatively charged electrons are pushing the other electrons away. And so in this second shell, you can have 8 electrons all whizzing around trying to get towards the center of the atom, but they're all being repelled by the 2 in the actual middle. After that, you've got another shell of 8 electrons. These ones are closer to the edge of the atom. These ones, if you give them enough energy, they're actually going to disappear. Bye! Now, when you look at the chemistry, you will know that actually these electrons want to exist in full shells. Atoms are very uncomfortable having non-full shells, so it only takes a little bit of energy to either get rid of an electron or add an electron to make the shells full. So if we have a look at this one, this carbon atom, currently it's got 4 electrons. Now this is a neutral carbon atom. In nature, it cannot exist. It's very unstable. The outer shell of the electrons has got 4 unbonded electrons, so it needs to bond with other things. Carbon is very versatile. It's like the Lego block of organic life, and that's because it's got 4 opportunities for bonding. We'll talk about bonding when we do the chemistry section, but just know at the moment that these 4 electrons are quite pliable. So what happens then if we pass some electromagnetic energy towards or at this atom? Here we go. Here is a photon of light. What it's done is it's come along and it's hit the top electron. The top electron's now got excited. It's got more energy. It's absorbed the energy of the light and it's gone, whee, I'm having that. And it's now closer to the edge. It's further away from the protons and it's close to the edge. Again, this is very unstable. It doesn't like this. It's got loads of energy. Imagine you've just entered your science lesson and you've sat down, but before the end of break, for some weird reason, you've just downed an entire bag of Haribo. You're now very uncomfortable. You have a lot of energy and you need to get rid of it. But unfortunately, you're sat listening to a large bearded man tell you about electrons. Now, what will happen is this electron will become de-excited. It will get rid of its energy and it will go back to where it was, where it's comfortable. It will go back to the previous energy level. And when it does that, it will release more energy. So off it goes, whee, releases its energy. So you end up with photons of light. And this is how we get neon lights. What we do is we fill a tube with neon and then we put really high voltages through it. And those really high voltages knock all the electrons about. And all those electrons then try their hardest to get back to their relaxed state. When they do that, they give off energy. Each atom gives off its own signature amount of energy. And so with neon, you get a lovely red light. With xenon, you get a fantastic blue light. Krypton is green. And you get these fantastic arrays. So you can have these tube lights which have different colours. Nowadays, we use strips of LEDs, but back in the 80s and 90s, neon lights were everywhere and Vegas was full of these fluorescent tubes, and it was absolutely gorgeous. Moving on to background radiation. If you go off walking across the moors, I'm thinking of Dartmoor because I'm in the middle of Devon at the moment, and Dartmoor is literally over there. I can see it from my window. If I go walking over Dartmoor, I'm going to be walking over granite deposits. And as you go to the tors, which are basically very large hills where the weathering has worn away some soil and left basically the bones of the earth, the granite rock still standing, exposed. Now, these granite rocks are radioactive. Granite contains a very small amount of uranium, and in fact there is a uranium mine not very far away from here. Probably explains a few things, but the uranium mine over here is where they've dug out larger deposits of uranium from the granite. It wasn't very profitable because it's not enough uranium to sustain a business, whereas in Australia, in Canada and Siberia there are much larger uranium deposits. But these uranium deposits are highly radioactive. They decay and they give off a gas called radon. Radon gas is fine on its own. It's perfectly okay, and it will seep into houses and it will come up through the floor, through the bedrock of the foundations, through little cracks and things, and it will seep into basements or the ground floor of houses. If a house is very well ventilated, the radon gas will then just float away off harmlessly into the world where it belongs. However, if the house is not well ventilated, and there's a big problem in the 70s and 80s where basements were, when we didn't realize this was a problem, basements were getting filled with radon gas. Now radon gas is radioactive. Still not so much of an issue. Unfortunately, when it decays, it becomes a dust of thorium. Now that is nasty, because if you ingest this or breathe this in, this dust, now you've got an alpha source inside you, and I'll talk about why that's really bad in a moment. So around us we have got lots and lots of sources of radiation. Oh my god, Mr. E, are we being irradiated all the time? Yes we are, but we've always have been. Now let's have a look at this breakdown. 50% of the radioactive material around us is this radon gas, and this comes from the planet itself. There's nothing we can do about it really. As long as we don't let the gases build up, we're all fine. 13% of the background radiation, the radiation that we see all the time, is found in buildings, because if we've taken rock from the ground and made buildings out of it, or we've taken soil and turned it into clay and made bricks, these are still going to be radioactive, but only very slightly. So the buildings we live in are also radioactive. This is where we get quite a lot of our background radiation from. Other natural sources of radiation are things like cosmic rays. The sun gives off radiation all the time. There's radiation coming in from space and weird stuff. Cosmic rays are bombarding the planet. The magnetic field around the planet is really good at repelling a bunch of these, but a lot of it gets through, and this stuff is irradiating us all the time. Now at this point you're probably starting to worry and starting to panic, and you're going to turn to your mum and say, "Mum, Mr. Ree says we're all being irradiated by radiation all the time." Well, yes we are, but we always have been, and it's not so much of a problem. We'll move on to dangers of radioactivity in a few lessons time, and I'll talk about why cosmic radiation and background radiation is barely noticeable. The most surprising one on here for some people is food and drink. Food and drink is surprising because, well, we eat it and drink it. Why am I eating radioactive things? And one of the most radioactive things you could eat is a banana. Bananas grow in potassium-rich soil, and they draw in the potassium, and that is what you want the banana for, because we need potassium to help us grow. It's one of the minerals that we need. Unfortunately, a very small percentage of the potassium that we consume is actually radioactive, just like carbon-14 is a very small percentage of all of the carbon in the universe. The potassium that is radioactive is also a small percentage of that. And so when we eat bananas and other potassium-rich foods such as Brazil nuts and low sodium salts, they all contain potassium and are radioactive. And it's not the only radioactive source in food. But all of these things are natural sources of radioactivity, and in fact don't actually do that much damage. If you think of a world back before the 1940s, back when the Second World War was in full swing. Now, we lived in a pre-atomic age, an age where we hadn't developed nuclear weapons and we hadn't really developed nuclear power. They're still theoretical and they were developing these things. And then we started nuclear testing. The nuclear testing gave off a lot of radioactive particles. So now we're starting to include our own version of radioactivity into the background. And just like all things, if you think about diffusion, we have a high concentration of something and it will naturally shift to a low concentration. Nuclear waste and fallout is the same. So if you have a giant explosion like Chernobyl or Fukushima, that yes, is going to infect the local area, it's also going to spread radioactive particles around the world. Now, this has only contributed about 1% of the background radiation so far, so that's not so bad. But if we keep going, it's going to get bigger and bigger. And the biggest percentage of man-made radioactivity is from medical physics. So if you're near a hospital, there's probably a bigger chance of you getting a radioactive dose than anywhere else. And this is because we have X-ray machines and magnetic imaging machines, radiotherapy, all of these things. And they do emit some radioactivity into the rest of the atmosphere around it. This background radiation is not harmful. There is such a small chance of something going horribly wrong because of radioactivity that's come from the back. In the early days of discovery of radioactivity, they had some rocks which would glow slightly under certain conditions, under UV lamps and things. And they thought, oh, this is quite interesting. And they would leave it in a drawer. Now, one day, a scientist, I think it was Marie Curie, left a rock on top of some photographic film. And when they developed this photographic film, they found that actually the shape of the rock had been burnt into the film. And they realized that the rock was giving off photons of energy, just like light. And it was giving off what we call gamma rays, which I'll talk about in a minute. So these rocks were giving out different particles which were causing the photographic film to develop. So you're able to detect a radioactivity with photographic film. Nowadays we can have nowadays we have substances that just change colour if they get too much radioactivity. And we wear these are called radioactive shields. And you wear them as a little badge. So if you're a worker in, say, a hospital and you are an X-ray operator, you will have one of these badges. And every time it receives a dose of radioactivity, it will change colour slightly. And once it's changed colour too much, then you're not allowed to do any more work with radioactive sources for a set period of time because you've received a certain dose. Remember that we're receiving doses of radiation all the time from the background. We can also receive more radiation before it becomes dangerous. For example, if you break your leg, if you don't want any more radiation, you can't get an X-ray. So if you break your leg, or if you break bones 1,000 times in a year, at some point they're going to stop giving you X-rays because you're getting too much radiation. Think about that next time you're off in the skate park. The more famous way of detecting radiation is with a Geiger-Müller tube or a GM tube. You'll probably hear of it as a Geiger counter. Now, with this, it is essentially a tube of gas that when a radioactive particle comes into the tube, it knocks off some electrons and it turns it into an ion. This ion then makes the Geiger counter conduct electricity. That small conduction is then counted. And that is how they count the radioactivity of something. Now, a GM tube, let's pretend this mouse for a moment is a GM tube. If I hold it towards my light there, then what's happening is the radioactive particles from the light are going to come into the GM tube and it's going to form an ionization. I'm going to get a count and I'm going to say, ooh, a count. Now, what I need to do, because of background radiation, is before I expose it to the light, I need to find out how much radiation is in the room. So I'd allow it to just sit there, not looking at anything particularly radioactive, and just find out what the background count is. Then I would put it at my radioactive source, do the count again, and take away the background count. Sometimes this thing will just do a couple of clicks, click, 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 and then other times it will go berserk. And that is what you're seeing when you're seeing things in the films. or YouTube videos where they're coming out with Geiger counters and it's going click, 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 and it's going absolutely berserk. What's actually happening is each one of those little clicks is a radioactive decay happening. All right, so what are these radioactive particles? If you remember, there are three main types of radioactive particle that you need to know about. There are alpha particles, beta particles, and gamma particles. Your alpha particle is actually a helium nucleus. It's 2 protons and 2 neutrons, and that's it. There's no electrons around them, so it's not an atom, it's just a nucleus. So these things drift off, but they don't go very far. If you fire them into the air, they will only go a few centimeters, and that's because they're massive particles. They have a mass of 4, because it's got 4 nucleons. So off they go, 4 nucleons, not going very far, and then just kind of dropping off. These things cannot penetrate very far either, because they're big. Sorry. These things cannot penetrate very far either, because they're relatively big. If you take a piece of paper, very thin piece of paper, an alpha particle will come along and get blocked by it. It will actually bounce off and it will stop the alpha particle. Now we know that if you get a very thin piece of gold, what will actually happen if it's a couple of atoms thick, well, it will pass straight through mostly, or bounce back a little bit, or be deflected. And that's because actually if you roll out the gold very thinly, it will pass through, and if you get the paper to the same thickness as a couple of atoms, it will also go through. But paper is made of weird random pulp and bits of wood in different arrangements, so it's harder actually for the particle to go through. A beta particle. Now, an alpha particle comes when a nucleus is just too big. It's an isotope that is not very stable. Let's think about uranium for a moment. Uranium has 235 particles in its nucleus. That is not good. 235 particles all crammed together. This is where I use my bee analogy. Imagine for a moment you have 239 bees all crawling over each other. They're crawling and they've formed this massive ball of moving bees. This is what a nucleus is like. Now, some of these bees, let's imagine that 95 of them have stings, and these 95 can't go anywhere. These are the protons. These main bees, these 95 bees, are floating around. That's what makes the uranium uranium. The other bees, the worker bees that don't have stings, are now just crawling all over them. But what's happening is this ball is too big. There's too much heat being generated. The bees are getting uncomfortable and they're just kind of buzzing around and not liking it. So what they'll do is they'll eject 4 bees. They'll just go, nope, brah, you 4, get out of here. And they'll take 2 bees with stings, 2 bees without stings, and off they go. And they'll form their own little ball of bees. And off they go. That's the alpha particle. And then this new nucleus, this plutonium nucleus, which has just lost 2 protons, so therefore is 4 nucleons lighter, but because it's lost 2 protons, it's now a completely different element. And this thing is much more stable. It's still radioactive, it's still going to decay and spit something else out, but it's much happier. That's how alpha particles decay. Think about beta particles. Beta particles are small electrons. These things happen when actually a neutron decides it doesn't want to be a neutron anymore. It wants to be a proton. And it can do this by losing some negative charge. When it loses some negative charge, it becomes positive, like a proton. So a neutron can all of a sudden be sat there going, hey, no charge for me at the bar because I'm neutral, yeah. No, now I'm positive. Get gone, you negative beast. And it'll fire off some negativity in the form of an electron. Bing! Off it goes, ejected from the nucleus. This little electron can actually fly quite far. It's got mass because it's an electron, but not too much. And actually, if you have a thin sheet of metal, that will stop it. It will pass straight through your paper and it will get stopped by thin sheets of metal. And we use this actually to measure the thickness of paper. If you fire beta particles through paper that's too thick, actually does start to get stopped. And we don't want that. And if it's too thin, too many beta particles get through. It's one of the uses of radioactive materials. And again, we'll go through that in a different video. Positrons are the antimatter versions of electrons. These are small positive charges. Now this happens when a proton decides it wants to be a neutron. It goes, no man, I'm not so positive anymore. I'm kind of meh. So your proton, who's all positive and buzzy, yeah man, I'm a proton, yeah, positive, all of a sudden goes, meh, meh, I'm feeling meh, meh, and becomes neutral. To do that, it's got to get rid of its positivity. Go away, positivity. And the positive charge goes off as a particle. A little positron has exactly the same mass and all the properties of an electron, except it's a positive charge instead of a negative charge. Now the fun occurs when a positron comes along and meets an electron. They're exactly the same particle, just one's positive, one's negative. If they meet, boom! You get a massive release of energy. These particles annihilate each other. All of their mass becomes energy. And join me in an A-level physics video later to find out how cool that is. It's awesome. We're going to end this section by looking at this exam question. If you have a radioactive source and you don't know what type of radiation it's emitting, you could do a series of tests. And with these tests, you could find out exactly what type of radiation you're looking at. Given the explanations of the radioactive particles I've just given you, can you work out the answer to this 6-mark question? Now remember, there are 3 types of radiation. So just listing a couple of points about each type and how you test it is probably going to get you 6 marks. Don't be afraid of 6-mark questions. Normally, just bullet pointing the things you know is going to get you a decent mark. Just being able to connect those bullet points in terms of actual writing is what's going to convert that into 6 marks for you. So what I want you to do, pause the video and have a quick go at this question, and I'm going to go through it in a moment. No cheating now. Alright, welcome back. I'm going to trust that you paused the video and had a look at this yourself. Now, let's have a look at the answers. Remember, we're testing for the penetration through materials and their range in air. Now, the easiest thing you can do is you can take your Geiger-Müller tube and you can put it next to your radioactive source and you'll get some counts. And as you move it away, the counts will decrease. And the further you move it away, should start to tell you what kind of particles you're dealing with. If you've got alpha particles, which remember only fly a few centimeters in the air, then as you move the GM tube away more than a few centimeters, you're not going to detect any particles anymore. Also, alpha particles cannot penetrate through paper. So if you put a piece of paper between the detector and the source, then you're not going to get any radioactive counts. And this means that if any of these things are true, if paper blocks the counts, or if moving it too far away blocks the counts, then you're dealing with alpha particles. Similarly, if putting paper in the way and moving it a few centimeters slows the count but not very much, then you may be dealing with beta particles. So you use a thicker material, put a piece of metal in the way, see if that stops it, and then move it even further away to see if that stops it. And if you're about a meter away, the beta particle is not going to reach the detector anymore. if your counts dramatically drop off, you've got beta. So I've just realized the PowerPoint went gamma first, then beta. That's not very helpful. But anyway, gamma rays are the same. Gamma rays normally die off around about 2 meters. When we're doing demonstrations with radioactive materials, all students should be, and other members of staff should be 2 meters away from us and the source. So if you've taken the detector more than 1 meter away and you're still getting some counts, you're still getting counts through thin pieces of metal, then what you'll do is you'll put thick pieces of lead over the source, and you should then see it drop off completely, and that means you've got a gamma ray. So all you need to do is just describe doing that, just bullet pointing these, likely to get you 4 or 5 marks. It's then describing what's in between that will get you the extra mark. Alright, thanks for watching. Don't forget to like the video, subscribe to the channel for more content, keep an eye on this playlist. I'll expand it through the dangers of radiation, and I will do more content for those of you doing separate science and separate physics, so that you've got the full range of CP6, because after this point we diverge slightly and there's more content for you. You'll now see a bunch of different videos being advertised on here, so please click one of them. You'll also see my face here. This is for you to subscribe to me, and if you see my face here, cartoon version of my face, that's if you want to go and watch me open some Pokemon packs, which I highly recommend if you've got some downtime. Right, all that's left now is for me to say stay safe, see you soon.